Alright, in this video we are going to talk about integrating factors. But before we see a description, let's look at example first. So example, let's suppose that I have a differential equation 3e to the x times y dx plus e to the x dy equal to 0. This is a differential equation in the form mxy dx plus nxy dy equal to 0. Well, let's start by try to use an exact differential equation technique. So I'm gonna let m to be this thing. I'm gonna let n to be this thing. And then once I set up m and n, so I differentiate m with respect to y. So what I get is 3e to the x, and I differentiate n with respect to x, so I get e to the x. So m subscript y is not equal to n subscript x, so this differential equation is not exact. So you cannot use exact differential equation technique. But what you observe from here is, well, my equal to 3e to the x and x equal to e to the x. They are so close. They just miss some constant. So, well, if I delete everything here and then I say, okay, start over. And then now we're gonna multiply the original equation by e to the 2x. So I multiply the original equation by e to the 2x on both sides. So on the left hand side, my transform differential equation, it's going to be 3 times e to the 3x times y dx, and then plus e to the 3x dy equal to 0. Alright, now let's check the exactness of this differential equation. So I will let m to be this thing, and I will let n to be e to the 3x. Now if I differentiate m with respect to y, so I get 3 e to the 3x. I differentiate n with respect to x, so I get, well, differentiate e to the 3x, you get e to the 3x, but by the chain rule you have 3 here. So now my equal to nx. So this differential equation is exact. Wow. And then after that you can use exact differential equation technique to solve this differential equation. So you can see now that if you multiply by e to the 2x, it changes the world. It transforms your original differential equation to exact differential equation. The function e to the 2x here is called integrating factor. Now let's take a step back and look at a formal definition of an integrating factor. So if you start from a differential equation m dx plus n dy equal to 0, and you can find a function mu such that when you multiply mu to this differential equation m dx plus n dy equal to 0, and then it's transformed the differential equation to exact differential equation, then such a function mu is called an integrating factor. So this integrating factor is a key to solve this kind of problems. On the next slides, we're gonna learn how to find an integrating factor by using a theorem. But well, to sum up, integrating factors turn non-exact differential equations into the exact ones. So let's look at a theorem. So theorem, given that we have a differential equation mxy dx plus nxy dy equal to 0, then we have two conclusions. First, if you compute m subscript y, subtract n subscript x, and then you multiply it by 1 over n. If this thing is just a function of x, well, we call this thing fx, then the integrating factor is mu equal to e to the integrate fx dx. So this is the first conclusion. So if you start by computing m sub y minus n sub x, and then you multiply 1 over n, and then you see that what you have left is just a function of x called fx, then your integrating factor is mu equal to e to the integrate fx dx. This is going to be useful when you work with the real problems. All right. Another case is the second conclusion. Well, if you compute n sub x minus m sub y, and then you multiply by 1 over m. If this thing you compute it, and it's just a function of y, well, you can call it gy. Then the integrating factor for this case is mu equal to e to the integrate gy dy. Alright, so you have two ways to do it. So the second case, if you compute this quantity that I highlight in light blue, and then if it's come back to a function of y called gy, then your integrating factor is e to the integrate gy dy. Alright. Well, I will show you examples. Alright, example 11. Find the general solution of 3xy minus y squared dx plus x times x minus y dy equal to 0. First of all, you can see that this differential equation is of the form m xy dx plus n xy dy. Alright, I can let m to be 3xy minus y squared and let n to be x squared minus xy. Just simplify a little bit. So the first step is I am going to compute partial derivative of m with respect to y. So here I differentiate 3xy minus y squared with respect to y. So I get 3x minus 2y, right? And then I differentiate x times x minus y, which is the same thing with x squared minus xy with respect to x. So n subscript x, this is going to be 2x minus y. Well, m subscript y is not equal to n subscript x, so this differential equation is not exact. However, if you look at my minus nx, so what you have is 3x minus 2y minus 2x minus y equal to x minus y. Well, luckily, if you try to multiply this quantity by 1 over n, so 1 over n times my minus nx, this is going to be 1 over x times x minus y times x minus y, right? Because your n is x times x minus y, and then your my minus nx you compute before, you have x minus y. And you can see that x minus y cancel. And then what you have left is 1 over x. This is just a function of x, right? We're gonna call this thing fx. So let fx equal to 1 over x. So now this thing match with the condition of the theorem that we just discussed on the previous slide. So if I have a situation like this, so the integrating factor is mu equal to e to the integrate fx dx. So that is e to the integrate 1 over x dx, and that is e integrate 1 over x dx. I get log absolute x. So for here, I'm gonna ignore absolute value a little bit. So just assume that x is positive, and then also ignore the constant term. So I will have e to the log x, which is x. So our integrating factor for this question is mu equal to x. So we're gonna multiply mu into the original equation, and that will turn the original equation from non-exact differential equation to exact differential equation. So let's do it. So if I multiply the original equation by x, so now the transform differential equation is, well, multiply everything by x. So I have 3x squared y minus y squared. Oops, sorry, I forgot x. So again, I'm gonna multiply everything by x here. So I multiply everything by x here on both sides. So what I'm going to get is, so let's keep the red pen here. So I have 3x squared y minus xy squared dx, and then plus x cubed minus x squared y dy equal to 0. Well, this is the transform differential equation. Now let me copy this differential equation to the next page. So copy, and then here we go. So now we are going to solve this differential equation. So let's start by again setting this thing to be mxy, setting this thing to be nxy. Just make sure that this is an exact differential equation. So m sub y, this is going to be 3x squared minus 2xy, right? And then n sub x, this is going to be differentiate with respect to x. So you get 3x squared and then minus differentiate x squared y with respect to x, so I get 2xy. Alright, that's perfect. So my equal to nx. So if I call this differential equation star, so it's implied that differential equation star is exact. Now it's time to solve this differential equation. So again, because this is an exact differential equation, the general solution is of the form fxy equal to c, right? And we know that, well, if you differentiate f with respect to x, so you're gonna get m, and if you differentiate f with respect to y, you're gonna get n. F is equal to integrate mxy dx, and then that is integrate 3x squared y minus xy squared dx, right? Because this is my m, so I just take it here, and then that is, well, integrate with respect to x. So on the first term I have 3y, this is constant, and then x cubed over 3, and then the second term I have y squared as a constant, so I integrate x, so I get x squared over 2, and then plus a function of y. Alright, and then just make it more clean, so this is going to be x cubed times y minus x squared y squared over 2, and then plus hy. Alright, this is my f. If I differentiate f with respect to y, so I should get back to n. So f sub y is, so differentiate this function that I circle here, and then with respect to y, so I have x cubed minus x squared over 2. This is constant, and then times 2y. Alright, and then plus h prime y. Well, this thing is x cubed minus x squared y plus h prime y. Alright, and this is supposed to equal to x cubed minus x squared y, right? Because that is my n. And this implies that h prime y equal to 0. So the function h, well, this is just a constant. Let's say c1. So we have everything here. So we put them all together. So we're gonna have fxy equal to x cubed y minus x squared y squared over 2 plus a constant c1, right? So the general solution of this differential equation is x cubed y minus x squared y squared over 2 equal to c. This is the general solution for this question, because you can group the constant c1 with c, right? Because we have the general solution of this form. All right. You can see that in this example we can convert non-exact differential equation to exact differential equation by using integrating factors. Well, when you face a problem at first, like example 11, well, it is your choice. So some of you say that, well, it is easier to use homogeneous differential equation. Well, you can. So one question, you can use multiple techniques to approach that problem. So for example 11, it can be solved by using integrating factor, and it also can be solved by using homogeneous differential equation technique. Well, but the answer must be the same. All right, so let's move to example 12. This is the last one for this video. Example 12, find the general solution of x plus y sine y dx plus x sine y plus cosine y dy equal to 0. All right, let's start by setting this thing to be m. Set this thing to be n. All right, and then differentiate it. So differentiate m with respect to y. So I get, well, I have to use product rule here. So keep x plus y, and then differentiate sine, I get cosine, and then plus sine y, differentiate x plus y, so I get 1. All right, this is by the product rule. And then differentiate n with respect to x, so I have, well, differentiate x sine y with respect to x, so I get sine y, and then differentiate cosine y with respect to x, so I get 0. All right, so this is just sine y. And then now you can see that if I compute n sub x minus m sub y, let's see what happened. So I'm gonna have sine y minus x plus y cosine y, and then minus sine y. So sine y cancel. So what you have left is minus x plus y cosine y. And then, well, if you multiply this thing by 1 over m, so you can see that it is 1 over x plus y sine y times minus x plus y cosine y. So what you have here is something cancel. So x plus y cancel, and then you have left negative cosine y over sine y. Well, this is actually negative cotangent of y. Well, this is just a function of y, right? We're gonna call this thing gy. All right, and then once we have this, so the integrating factor by the theorem that we discussed, well, few slides before, so is mu equal to e to the integrate gy dy, right? And that is e to the integrate negative cotangent of y dy. Integrate cotangent of y, this is log sine y. So that thing, so I will get e to the negative, so integrate cotangent of y, so I get log absolute sine y, right? Well, we're gonna ignore the constant term first, and then we're gonna ignore absolute value too. So this is just say sine y. So assume that it is well defined. So here, well, I can move negative sign up. So negative sign here. So I'm gonna move to the exponent. So what I'm going to get, I'm going to have e to the log of sine y raised to the negative 1, right? And then that will be just 1 over sine y, because this thing cancel e and log. So I have sine y to the negative 1, and that is 1 over sine y. So this is my integrating factor. So we're gonna multiply this thing to the original equation, and then it will turn to exact differential equation. All right, now we have x plus y times sine y dx, right, plus x sine y plus cosine y dy equal to 0. This is the original equation. So I'm gonna multiply by integrating factor, which is 1 over sine y on both sides. And then on the right hand side, you can see that this is completely 0, right? Because, well, 0 times everything is always 0. And then on the left hand side, you have something to cancel. So, well, once you multiply sine y into this differential equation, so you have just x plus y dx plus x plus cotangent of y dy equal to 0. Well, this is what you have after you multiply 1 over sine to this differential equation. And then let's check that this differential equation is exact. So you have this to be m, you have this to be n. All right, now your m differentiate with respect to y, so you get 1, right? And then if you differentiate n with respect to x, so you get differentiate x, you get 1, differentiate cotangent y with respect to x, so you get 0. So this is 1. So now this is exact differential equation. So good. Well, now our differential equation turned to exact differential equation, and then now you can solve it by using the technique that we learned before. So the general solution is fxy equal to c, right? And we also know that if you differentiate f with respect to x, so you get m. And if you differentiate f with respect to y, you get n. So we're gonna start by f is equal to integrate mxy back with respect to x. So that is integrate x plus y dx, right? And that is integrate integrate x dx, you get x squared over 2, and integrate y dx, you get xy, and then plus some function of y, right? And then after that, you have to check that once you integrate when you differentiate f with respect to y, it should go back to n, and that function f here, so we're gonna differentiate with respect to y, so that will give me 0 plus x, right? Because differentiate xy with respect to y, so you get x, and plus h prime y. All right, and my function n is x plus cotangent of y. So comparing this equation, so what you will get is h prime y equal to cotangent of y, and that is hy equal to integrate cotangent of y dy. So now you have log absolute psi y plus constant c1, right? So now once you have everything, so your conclusion is fxy is equal to x squared over 2 plus xy plus log absolute psi y plus c1. Well, this is your function f, and then you already know that the general solution is of this form. So the general solution is x squared over 2 plus xy plus log absolute psi y plus c1 equal to c. But you can group c1 with c because they are constant. So this is just equal to c, and that's all. This is your final answer for this question.